point out that the sun shines down its power to all the world and makes the wind blow strong as it will. I want to hope gentle rains can fall upon the land, so lovely earth can stay lovely still. Okay, so what we're going to do now is we're just going to continue, but bear in mind, nobody saw what we just did. So we're starting from scratch.
Okay.
Okay, so I'm going to start again, okay?
Yeah.
I'd just like to, I'm going to try to take the topic bigger than Bensonwood.
Yes.
I am not, I don't want to be here to sell Bensonwood.
Yeah.
I want to be here to educate people about carbon.
Well, this is one of the things, and
materials.
actually we're going to say that while we're going to, let's start, you say that first, okay? All right, ladies and gentlemen, welcome back to another Energy Week special. Extra, that's what they call them. Today we're talking with Rheannon and Chris, who have come from over from Bensonwood, which is in Walpole. New Hampshire. And this is an interesting organization for a bunch of reasons. What they're doing is they're building very efficient, very costly, but not necessarily very costly, housing for people who want to have new houses built. And it's using a system that was put together by Ted Benson. And we'll just go into that. And Chris, you had just said something. I'd like you to repeat that if you would.
Well, I hope to take this conversation bigger than Bensonwood. I'm obviously interested in our company being financially successful, but that's not my mission here to sell Bensonwood by any means.
Right.
What I'm, as a structural engineer who deals almost exclusively with wood, I'm hoping to take a couple minutes and help educate people about the benefits of timber construction from a climate perspective.
Right. And this brings me back to something that I noticed about Ted Benson, which I think is really interesting. Ted Benson being the founder of this company. And that is, I did an article about Bensonwood for Green Energy Times. And when I did that, I talked with him. And one of the things that I was impressed by is that he's been developing technology. He's been developing a business plan. He's been developing a production plan. And he's willing to share all of this with anybody who wants to do the same thing. So there's no big secrets here, which
Open
means
source.
Open source.
And
Open
Ted
source.
Benson is not going to fire you because you say, I'm interested in educating people.
No, actually, he wants us out here. He wants to change the world. That's
he
why
wants to save the world, and
Yeah.
this is what I was referring to in the Energy Week show.
Elon Musk of Wobble.
There you go.
There we go. Okay, Chris, tell me about it.
Well,
Let's start with wood.
let's start with wood.
Let's start with timbers. What's timbers?
Timbers are, by definition, 5 inches or bigger in one dimension. So 5 by 5 is really where you start looking at timbers. Historically, timbers came out of large trees. Very large trees, some of them, and they were built. They were used here to build barns by the settlers, the colonists. Eventually, that sort of morphed into mills and cathedrals and larger buildings, and even some houses. Although a lot of those have sort of come down at this point. They were replaced as sawmill technology changed with basically the Industrial Revolution, being able to take what the the forest resource was at that time, which was smaller and smaller trees because we were cutting down the bigger and bigger ones, to turn those trees into smaller dimensional material, 2x4, 2x6, 2x8. And that's really what we call stick framing or dimensional lumber framing. So the way that we built prior to the Industrial Revolution was quite different than the way that we built from the Industrial Revolution through up until today, where really, in terms of the housing of our country, is more delivered through a on-site 2x or stick framed construction method, which is not a very efficient way to build a building. It turns out that it's not very easy to insulate that building because when you're putting a lot of small parts together, there are obviously cracks and leaks through that building envelope. And so when Ted moved up to this area in the 70s, as he was starting the business, he got into taking down a lot of old barns on the side, and he realized how strong and how amazing these timber frames were. And part of the deal he made with a lot of people was he got to keep that material. So when he got a new job, eventually he was able to use some of the timbers that he had taken down and sort of reinvented or reinvigorated this craft. And there were a couple other people in the 70s who were doing this, but really he and a few other people were the sort of the fathers of the modern timber framing movement. He wrote a number of books, and it kind of took off from there in a niche market, and it really became very sought after for the high quality, the beauty of the exposed timbers, and I think that is what drove the costs up, is that it was just serving a higher end market. But that wasn't what Ted got into it for. He really got into it to create a better way to build. He wanted to build in a factory where climate control and precision machinery can be employed so that you spend less time on site, and then you can create a safer environment on site. And you can build larger members that come together rapidly so that you have less seams. So he started with the frame, but pretty quickly he moved into the enclosure system, where he and Amos Winter really helped develop the foam core structural insulated panel business, and for a number of years in the 80s and into the 90s, timber frames were, and still are largely outside of Bensonwood, wrapped in a foam insulation skin, which is a highly efficient building, usually somewhere between R30 and R60, or the typical, usually somewhere between R30 and
That's
R60 for the enclosure. Yeah, a typical dimensional lumber fiberglass might be rated at R19 and perform around R9.
And it sounds like what you're working on here is an aim toward there's a couple of different standards that are interesting, and it's kind of interesting to think about each of them. One of them is the net zero building, where the building actually produces at least as much energy as it needs during the course of the year. And the other one is the passive house, which is a different standard in which the house doesn't need energy inputs for heating, and so the house is heated by the body heat of the people, the dog, the light bulbs, even if they're LEDs, the computer, and cooking. And these standards are coming into the market now in a way that they never could have in the past. And one of the things I want to mention also is that I did an interview not very long ago for Green Energy Times, which involved an architect in Brooklyn. And he said to me, you can build a house today. And he had this in an apartment building that he had built in Brooklyn. You can build a house today. He said, a passive house is expensive. But you don't have to do the whole thing. You can go 90% of the way to a passive house at no additional cost over conventional construction. So you can cut your energy bill by 90% without changing the cost of your construction right from the get-go. And this is the kind of thing that we're talking about. What we're talking about is the structural strength and the age characteristics, the ability to last over a very long time of the classical barn, as you pointed out, the cathedral and so forth, and combining that with really modern standards, not just for efficiency though, but for also for construction. The business of building the building in the factory to avail yourself of efficiencies of scale, and then take the material out to the field for assembly.
Yeah, a good example of that is that we install our windows inside of our walls in the factory. And so we are able to deal with all of the edges of those windows and how they intersect our panels in a climate controlled way. So any foams that we're using to close up those gaps are definitely going to cure because it's 68 degrees in there. Whereas if you're trying to do that here in Vermont in November, that foam may not cure. Or if you're trying to do that when you're on a ladder from the outside with the rain pouring off the eave and a mosquito in your other ear, you might get a little distracted. But if you're standing on a level ground, it's safer and it's going to perform better in the long term.
And this means that working in your factory, it kind of implies that you're working in an air-conditioned space.
Well, not air conditioning.
What I mean by air-conditioned is that the temperature is controlled, the humidity is controlled, and it may not be the coolest place, but it's certainly not going to be the hottest.
No.
It has the best music, though.
It does.
What do you play?
I think the guys in the shop they have a rotating system.
Yeah, it's a
of
very
who-
eclectic mix. So you
Yes.
could hear just about everything anytime you're going through there.
Do you
From
hear
classic
Stefan?
rock and roll to some good old soul to some, old-fashioned hip hop.
Anybody putting on
Little reggae.
Some reggae.
Stefan Grappelli?
Sure.
Oh, I would love Stefan Grappelli.
Now you see, I know you people have got
Not
good
enough
taste.
VPR is played in the VPR classical would be great. For
I
us.
saw Stefan Grappelli live in Boston in 1996, and he was as good as he was when he was 30.
Was he playing in a wheelchair?
No,
Because he did that at the end.
did he?
Yeah.
He was absolutely amazing. He had to be helped across the stage, and he clearly could not see very well with the lights in that dark room. But he was astonishing. He sounded like he did in his old recordings from the 1930s. And it was just there he was,
A master, truly a master.
truly a master.
Yeah.
Yeah. We are a little diverting from energy, although Stefan Grappelli had a lot of it.
Well, I'll tell you, what Grappelli did with the violin, our craftsmen do with our wood.
Wow.
You want to transition back to Bensonwood. The joinery and the detailing, not just in the timber framing, but the way that our systems approach to building. And so when I say craftsmen, I really extend that to our architects, our engineers, Rheannon, our energy analysis, our project managers, really sort of understanding the entire system and looking at it with that broad perspective allows you to say, well, if you made that window a little bit smaller, your heating system can be nothing. Or if you made that window a little bit bigger, your heating system would be nothing. It really depends on the situation.
Sure.
And
That means that you've got to do site analysis and know what the orientation is and so forth before that building is constructed in its parts in the factory. You have to know where it's going.
and know how you're going to get it there.
Yep.
Because
Wow.
there
That's a
are
good
roads
point.
that we deliver our buildings on where you can't get a truck down. And so if we're building in the factory and we build a panel that's too big to go on that road, we're in trouble. So it's really a whole approach to how do you design, build, and deliver a high quality enclosure system structure. And with that systems approach, we've almost put timber framing behind, because timber framing is not the best solution for every project. Certainly wood is going to be the best solution in our opinion, but the beautiful exposed heavy timber post and beam, that doesn't appear in all of our projects anymore. We're still definitely sought out for it on a number of projects, but many of our clients are, especially the Unity homes, are more interested in the performance of the building and the enclosure system than if they're heavy timbers with chamfers on the ends of the edges of the
So
timbers.
what is used for the Unity homes that are not?
Well, we're using timber, but we're using, instead of solid sawn 8 by 12 inch timbers coming out of large logs, we're using glue laminated timber. And the glue laminated timbers are made up of smaller dimensional lumber, like 2x4s, 2x6s, or smaller. And they're glued up in a way that maximizes the potential of each individual piece. So the pieces are machine stress rated to know how stiff they are or how strong they are. And by building up a beam, you can put the best material in the places where the highest stresses are. And so we can really optimize the use of the forest fiber in a way that solid sawn timbers never could, because they're complete. You
So
get
you're
what you
custom
get.
designing a beam.
In effect,
Yeah.
we're not we sub that out to our manufacturers who provide us the beams, but
Yeah.
we tell them what we
You
need.
tell them what to do.
Right. And these forests that they build these beams out of are much more efficient from a carbon point of view because the forests are faster growing, they're sequestering carbon, and they're replanted. They're always done with sustainable forestry. So they're replanted as much, if not more, than they harvest every year. So in effect, we're taking this carbon out of the atmosphere and we're sequestering in each one of our buildings.
Goodness gracious.
Who said that?
I don't know. Well, that's the business of structurally engineered beams also gives you one thing that you mentioned was where you want the stresses to be able to be taken up and what individual pieces of wood you want there. My understanding is that you can get beams that you'd never be able to get in nature.
Oh, absolutely. We've had beams or pieces of wood through our shop that were 8 feet wide, 12 inches thick, and 60 feet long.
Wow.
Holy!
You can't find a tree like that. Well, you can find one or
What
two.
do you do with a piece of wood like that?
Make toothpicks.
No, you know. What would such a piece of wood be used for?
Well, in that case, it turned into a 3-story shear wall, a wall to reinforce the building against lateral loads for an earthquake or a wind situation.
My conscience. That's impressive.
Yep. Maybe I can show you my PowerPoint.
Maybe you
presentation.
could, but you know what I'd like to do? I'd like to tell you a little story, and I don't remember where this came from. It might have come from Ted Benson. I love telling stories. There was a, and I wish I remembered who said this. There was a building in, I think it was an abbey in Europe, and they started to realize that the old huge beams that had made this thing had started to. Do you know this story?
I believe I do.
Okay, did it come from Ted Benson?
Probably where I heard it. Yeah.
Okay.
I'm not sure.
They realized that the beams were getting old. They were too old. And I actually lived at one point in a house not a house. It was a building that was built in about 1250. So I'm kind of familiar with what these buildings are like. They're different, but they were getting old, and they said, we've got to replace these. Where are we going to get something to replace them? And they had all kinds of people in who said, this kind of wood just doesn't exist anymore. And then they talked to somebody who came in and looked at it and said, but they're
university
out there.
historian.
They're out there.
Yeah.
A university historian. There you go.
It was
They're
for a
out
university building in England, I think.
It was a university building. That makes perfect sense. They're out there. What do you mean they're out there? They planted trees when they built the building because they knew that these things would have to be replaced. And they knew that they would need to have trees of that dimension. So they put them there with the idea that they would be there in however many hundreds of years it would take.
I think that story is relayed in Storbrand's How Buildings Learn. That's
Okay,
the name of that
great.
book, yeah.
I'm glad that
And Ted's older work is prominently featured there too as well.
Yeah, this is sustainable building is not a new idea.
That's stretching the word, but it's absolutely accurate.
However, it's an idea that appears to have been kind of abandoned at some point.
For
Less money, less
a couple of
profit.
decades at least.
If you think about medieval building, are you familiar with mud and wattle buildings? Mm-hmm. Okay, that is not exactly designed to be long-lasting. This is a building where you literally weave twigs together and then you cover it all with mud, and that's your insulation. That's what your wall is made of. And those were going into timbered buildings as well, but they were a little bit different. So we want to go to your.
Yeah. So I've given this talk a couple
If
times.
this is working properly,
I think I
it's
can.
in PowerPoint now. All you got to do is click
Okay.
it.
So
He's
I've
going
given
to need
this.
this if he's going to do that.
No, I'm just going to.
Well, I want to make sure that it doesn't make a lot of noise.
Oh, okay. So I've given this talk to some architects before, and to obviously people in our company before, and really what it's about is carbon dioxide. I'm not going to.
I should put that up on a screen, shouldn't I?
Yeah, you should.
There we go.
There you
Okay.
go. Okay.
Better looking than me, that's for sure. So if you go to this website, you can watch a 3-minute movie about CO2 concentration in the atmosphere. It was done by the good folks at NOAA, And I won't go through it completely, but we've been monitoring the CO2 in our atmosphere very closely since 1958. And it doesn't look too bad there. It looks like a nice linear curve.
Which will eventually go to infinity.
But if you, the question is, what's the slope of that curve, and
Yes.
what does it look like in the long term? So if you look at that over the long term, going back to sort of early man and woman, that and we can measure this by bubbles in the ice cores that they've
Yes.
been measuring. So these are different data points. You can see that it does fluctuate, and so people are always saying, well, global warming is a natural fluctuation, but really it never gets above 300 ppm until about, well, here's the Lascaux Art Cave. So let's zoom in on that orange bar, and you can see that even after Lascaux, through the Roman Empire, through the medieval period, I like to show, what we were doing with wood in the 7th century here in Japan. Carbon dioxide is still pretty low. And then, well, I won't blame this on the Declaration of Independence, but that's really when it starts to jump. So this is, sorry for jumping around here, but this is an infographic that was down in Boston this summer in a show that I'll talk more about later, but it kind of charts the history of trees over that time as well. And so 322 million years ago, trees started. And you can see that, we did a lot with trees, but right about here, 1830, lumber shipping, balloon framing, this is when the sawmills, the Industrial Revolution really started taking over. And in 1872 and 1871, there were two large fires in urban areas in our country that sort of turned people off of wood, the Chicago fire and the Boston fire. And that, combined with the cheap energy window opening, really started paving the way for steel construction or iron construction to come online in the urban environments. Now, when you think about that CO2 graph and you think about the world population growth, it actually is a pretty interesting mirror of one another. And so the question is, where is this CO2 graph going to go, and where is the world population going to grow? So this is the world population over the last couple thousand years. And here's the predictions out of the UN as to where we're going to go. Are we going to go on this red line and have 16 billion people? Or are we going to curve off, or are we going to have some major problem and start going backwards?
Or some other reason to start going backwards.
Right?
It doesn't have to be a problem. It can be a recognition of a problem that we might have.
Absolutely. And so we think that there is a problem with the carbon dioxide concentration at 400 ppm. We're starting, that scientists are saying, or 350 actually, scientists are saying that the 2 degrees C is pretty much inevitable at this point.
Right.
At 1,000 ppm, people start to get tired and have headaches, and so if we get to that point, we're definitely in trouble. So if we can argue about where the best point to be is, but we know we're on a bad track right
Yes.
now, and we need to do something
Yes.
about it. And so what we need is solutions. So a couple of years ago, the Carbon Mitigation Institute, a group out of Princeton, came up with a way to visualize the carbon problem. So here's the historical carbon emissions, and this is from 2010 to 2050 if we stayed on that same projection where we're headed. They took this triangle here and they said this is the theoretical stabilization triangle. If we can not put that triangle into the atmosphere, we can stabilize our climate, and then maybe eventually we can actually start turning around and getting into something that's more what we want.
The UN has said that in their best case projection, we would be in a carbon negative economy by 2060.
That would be wonderful.
So I think we can do it before that.
And that's probably where that is, 2060,
Yeah.
headed negative. And we need to. We need to for our kids and our grandkids and their kids.
Yep.
And So they took this stabilization triangle and they, like good engineers, they broke it down into smaller problems. They broke it down into 8 problems. And they called each one of those a wedge, and each wedge represents a certain amount of carbon. And these wedges are things that we have done as a global society that are demonstrated technologies that can be done. So this is, we can do this. And actually this is 5 years old. So
we can do this exclusively relying on technologies that we already have
exactly
developed.
what I'm saying. This is 5 years old, and the
Yeah.
technologies have changed at 40 cents
The
a
stuff
watt.
I'm seeing is just,
Yeah.
it's outrageous the way technology is changing.
So
And
we
yet
can do it sooner than 2050.
We can do, absolutely. I have no doubt of that.
So some of these are have problems or are expensive. Nuclear electricity takes a long time to build a new plant, but some of them are not that hard to do. Wind is not that hard to do. Solar is not that hard to do. Planting trees is not that hard to do. Efficiency is something that Rhiannon and I work on every day. Carbon capture, you showed the early thing earlier in the last show. And so really what it comes down to is understanding the carbon flows of our world. And you can see that pretty much everything is in balance until we start taking these fossil fuels out of the ground and burning them in our civilization and putting that carbon into the atmosphere. So what we're trying to do with wood is take this forest resource and turn it into long-term carbon storage. That obviously happens through
That's what's called sequestering carbon.
sequestering carbon, long-term carbon storage.
And the beauty about doing this, instead of pumping it into a hole in the ground that it's eventually going to escape from, is that while it's being stored, it has use.
We're
And
living
the
in
use
it.
is we're living in it.
And it's beautiful.
Yeah, and it's beautiful, and it provides for a comfortable life.
So this is how energy from sunlight turns into glucose, which eventually turns into cellulose inside of the plants. And so I've been going around telling people we're building these wedges, these 1/8 of a carbon of that stabilization trial for a number of years here. This is a project we built in Maine that had a bank of solar panels on the roof. It also had a bank of solar panels in an old abandoned tennis court nearby. And this project is net zero, LEED platinum, FSC certified, forest stewardship certified wood throughout. It operates with no annual electricity costs.
What
And this
about
is in
heating?
northern Maine.
Does that include heating?
Includes heating, includes everything.
Lighting,
Light-
heating,
everything.
that this
Everything.
person requires outside of transportation, probably.
This is not a person, this is an institution.
This is an
the
institution.
Coastal Maine Botanical
Oh, yes,
Gardens
of course. The
in Booth
Botanical
Bay, Maine.
Gardens, okay.
And we built this between them closing for one fall and opening for one spring. So we built this in the dead of winter in northern Maine, mostly in our factory.
Which is in New Hampshire.
Right, so you can see how we are modeling everything in CAD, and we take those sticks and we put them through a CNC process, and we build them up into our highly insulated large panels. And so this is what wood is. It's cellulose, which is basically 50% carbon by weight. The glucose molecules get bound together, they turn into cellulose molecules, they turn into these long fibrils and fibers, and those fibers turn into wood. They're basically big bundles of cellulose straws.
Which is why wood is strong.
Yeah.
Yeah. It's because you've got a lot of, not terribly strong, but very long and somewhat strong fibers
The superorganism.
that are all bound together,
Yep, they're all working together.
and that makes wood strong.
But we can also pulverize this wood and turn it into insulation, which we do now. We've sort of, I wouldn't say we've completely abandoned the foam core stress skin panels, but in a lot of our buildings, we are now using a cellulose insulated panels. So this is made out of old recycled books that get ground up and injected into our panels and give you very high R value, again R30 to 60, depending on thickness.
Do you use cloth for this, clothing? That kind of thing?
No, they do sell cloth insulation, but
Yeah.
this is old books that
This
grind
is
up.
old books.
Yeah, and the beauty of this is also when you're putting this insulation into the panels, some of it inevitably falls on the floor, right? So what do you do with that? Well, if that was foam, and it's curing, you got to put it in the landfill. But here we just sweep it up and throw it back in the hopper, and it goes into the next panel. So there's really almost zero waste when we're building these panels. And so I've been talking about these wedges for a long time, and I was so excited this March when an article came out in the Journal of Sustainable Forestry that really looked into, well, what can wood do on a global scale? How many wedges or how many tons of carbon dioxide can it fix? Or by using it instead of steel or concrete, can it avoid being emitted? And what they found was that, I'll just read it, it could save 14 to 31% of global CO2 emissions and 12 to 19% of global fossil fuel consumption using between 34% and 100% of the world's sustainable wood growth.
And sustainable is very important here.
Absolutely.
That means
important.
you're not wrecking forests doing
No,
this.
the wood that we get comes from forests that are replanted at a rate equal to or higher than they're being cut and used. So we really are continually fixing carbon from the
I want to point
atmosphere.
out something, and that is that I promised people that we were going to show how Bensonwood was going to save the world. And I think we're showing that.
We're getting close. But we don't want to be the only ones. Bensonwood, we're the tip of the iceberg. What we need is a movement here, and it's starting. It's starting in Europe, it's starting in Australia, and I want to show you some examples
I
of
think
those.
that Ted Benson should get some ping pong players and go to China.
Well, we have a rich history with Japan. We have not really made contacts in China, but it's not too far away. I do want to point out that there are lots of different types of forests, and if your only goal is to sequester carbon, you probably want to use this dense forest. But that is not our only goal. Our only goal is a sustainable planet and recognizing biodiversity, and the resources beyond wood that is in the forest is important too. So by using certified forests, we're allowing other types of forests to develop naturally and exist in this world. So in this article, they looked at how much energy it takes to make wood, how much energy is in the different types of gases and fuel. They looked at how much energy it takes to make steel, concrete, brick, aluminum, all
And
these
if I can
things.
stop you just for a second, concrete is one of the biggest carbon emission.
3 to 5% of global carbon emissions are due to the use of concrete, the annual use of concrete.
It's a very, very big, very considerable thing. And if we can reduce that, if we could reduce concrete use by 50%, which is conceivable, we could reduce carbon emissions by a lot. And in fact, if we did it properly, we could be reducing it by more because we'd be sequestering carbon in the process.
Exactly.
Right.
So this is a very, very big consideration.
And that's exactly what these graphs show out of this article is. So here's a wood I-beam versus steel I-beam. If we use wood I-beams instead of steel I-beams on a global sort of view, we can save 10 kilograms of CO2 per kilogram of additional wood used, and almost up to 10 here. And so that's the biggest payback for wood versus other materials.
Which is why you would go to a single piece of wood, which is a foot thick, 8 feet wide, and 60 feet long.
Right. That's where...
So when you're talking about I-beams now, you could be making skyscrapers out of wood.
We're going to get to those. They look at the forest management. We'll put this up, but don't flip back to it yet because I want to keep on these. So that's where we're going. We're going to wood skyscrapers, mass timber for dense urban environments.
This is amazing.
It's what we need to do.
This is really thrilling.
Yeah, it's exciting to be a part of this industry right now.
Yeah.
The innovation in wood technology has really evolved dramatically. It's almost, and maybe even more accelerated as the photovoltaics. It's just not as sexy. So people don't talk about
I
it.
was thinking something along the same
Yeah.
Well,
lines.
maybe it'll become sexy, and when it is, it'll become very widespread.
Right. So along with these new wood products, we've also got new connections, screws that are a meter long. I can buy a meter long, fully threaded screw now. That's incredible that I could do that. Why do you need that? That's a much more complicated thing. But we can build amazing
Look at
buildings.
that.
This is the
Oh
Cathedral of
my
the Christ of Light in Oakland, California.
Wow, that's impressive.
This thing has been built. This is
This
not
is
a-
built. This,
is
and to
not-
give you a sense of scale, the concrete at the bottom is 12 feet tall. These glulam arches are 128 feet long.
This is a building. This is
This is in Oakland, California,
Is
which is
that
a
a
seismic
photograph?
zone. This is a photograph.
this
yes.
is not an artist rendering.
No, this is a-
not somebody's wild imagination.
No, no.
It's real.
It's real.
This replaced the cathedral in Oakland that was destroyed in the, I believe, it was the Northridge earthquake. This was the third place design. They had the Catholic Church had a design competition, and the first place design went into design development, and they couldn't get the project in budget. So they went back to Skidmore, Owens, and Merrill, and they said, "Can you do this for the budget?" And they said yes, and they got the job, and
Look at that.
And they
Just
built it.
Look at the scaffolding on that.
That is
they
That
put up
is
this
amazing.
light fritted Oculus, and they brought these glue lambs down on the boat
No.
from British Columbia, because you can't truck something
Oh,
that
of course.
long.
How long are those things?
128 to 130
Those-
or
are
something.
Are those things called crucks?
You might call that a cruck, yeah.
Wow. You know,
That's a modern cruck.
This is a modern cruck. A cruck, for anybody who doesn't know, is you see those beautifully shaped woods, trees out in the woods, where the trunk of the tree is curved. And if you can find a bunch of those that are matched to each other, you can use them as structural members in a building where you have a curved roof. And they used to do that in the Middle Ages. Now these things are.
We make them to the shape we want them. Instead of growing those trees for 300 years like they did at that abbey.
This is astonishing. This is absolutely astonishing.
Obviously, Oakland is high seismic, so there's a lot of steel cabling that reinforces this thing, but it is an incredible space.
This is in a high seismic area on top of everything else. You're building a building here. How
And-
tall is that?
Well, that's 130 feet or something like that.
So you've got a building that's 130
150.
feet tall, 150 feet tall, that is made out of wood. The structural elements are wood. Pieces that are 130 feet long or something like that, that are curved. And the thing is going to withstand the kinds of earthquakes that you would have in California.
Yeah, absolutely. It has.
Or now that they've started all this fracking in Oklahoma.
Right.
That's almost worth taking a trip to Oakland just to see.
If you want to take a trip, go to Seville, Spain to see this building. This is the largest timber building by volume in the world right now.
You've gone back.
Sorry. Yeah, go forward again.
There. Whoop.
Well, here it is. It's called the Metropol Parasol.
That is absolutely scary looking.
Looks like a big fish.
It fills 6 city blocks in
Wow.
in
Oh my gosh.
Seville, Spain. It's got a museum underneath. These are concrete.
When you said that thing about this is like PVs or computers, I thought you were kidding.
Oh no.
Now I see you're not kidding.
No, no, no.
And what this can do for architecture is just mind-boggling.
The possibilities are endless for architects, and architects are not used to using wood in this way because we have been in this steel and concrete mindset for the past almost 100 years, or maybe 120 years. The architecture schools don't even teach wood anymore. The engineering wood schools barely teach wood, where students are required to take concrete and steel courses as part of a graduate engineering degree. There's very few schools that require a wood course.
Where did you get your training in wood?
I got my training in wood at Bensonwood.
How do you like that?
I got my formal training in school at Dartmouth College or Thayer School of Engineering, and
Right.
then at MIT.
Right.
And the physics of a building in an earthquake are no different whether it's wood or
Right.
steel or concrete.
Right, right.
It's just the details of the connections and how
Right,
that material
right. But
performs.
getting back to this thing in Seville, this is astonishing. That is utterly astonishing. I don't think a thing like that could have been done in
No, these
a
are
few years
these
ago.
are laminated veneers. So they skin trees into these thin veneers and they make panels. And then they were able to cut each one of these panels into a custom shape. And then they were able to completely coat the panels in a polyurethane coating that basically protects it from the elements, the sun, the wind, the rain.
So how long are these things going to last?
I think I heard it was about a 50-year lifespan.
Really?
Yeah, at least
That's
a 50-year.
disappointing.
Yeah. But they, no, well, I think they can touch them up in 50 years. I think
okay.
the building's not going to fall down in 50 years.
Yes, well, that's yes, that's true. But I would, if you had come back and said these things should last 1,000 years, I would have.
Well,
They might.
if it had a roof on it, maybe it would. But that is a
dear.
fully exposed wood element. So here's another in Metz, France. Shigeru Ban, Pritzker Prize-winning architect, made this beautiful woven wooden canopy that is just
Look at that.
incredible.
That is stunning.
what we can do with wood.
That
now.
is absolutely stunning.
I'm jealous of the poor engineers that got to look at all of these bolts and nuts and how they're connected. And
Well, this is why you want a screw that's a meter long.
right. Right. Here's a shot of that same area at night.
Oh, isn't that
connection
stunning? Oh
detail.
my goodness gracious! Oh,
Now we're lucky. We actually have a building in our country now that is.
yes. Well, this is.
Besides the Oakland,
Yeah.
this is a new museum in Aspen, Colorado that just opened
It looks
a month
downright
ago.
stodgy,
It's
doesn't it?
made out of well, the veneer here, though it looks like wood, is actually sort of a pressed paper.
I was
product.
going to ask you about paper and how that would function with all of this.
Well, I don't want to talk much about paper because I think there's a better use for that forest fiber than the pulp that we make paper out of. But
Yeah.
it's an architectural statement to create the woven basket appearance. But what I love about this building is the roof on the fifth floor. That's you go up and have a drink at in the bar. This is a 3-foot deep assembly of a two-way truss that has these sinusoidal waves that sort of are at a
Yeah.
45 degree to the main
Yeah.
top and bottom chords. And I think it's 50-foot spans in here.
Sinusoidal means curvy
Curvy.
in a particular way.
Yes.
A particular.
I think it's a
curve.
modulated sinusoidal wave, but
Okay.
don't need to get
We
technical.
don't have to get into details.
but this is Aspen,
I
Colorado,
just want
you know.
people who are watching the thing to understand what the word
Yep.
means.
Heavy snow load in a glass roof, flat, in Aspen. You're looking at the mountain,
Yeah,
spanning
it's a ski
50
runs, isn't
feet
it?
out of wood. And this is all wood. Obviously, the columns are steel. That was an architectural statement, but it was a pretty incredible project.
Oh my gosh! Look at this.
Here's a soccer stadium in Germany that this wonderful engineer, if anybody wants to learn about wood engineering, look up Julius Natterer. He's really, or the modern father of timber engineering, in my opinion. But this is a soccer stadium that used solid logs for the main primary support structure, and then I believe glue lams on top. And actually, this project used a timber concrete composite shell roof system. So on top of the wood decking, they were able to pour concrete to create further spans and give it more protection. And so what I'm showing here is called cross-laminated timber, and this has been the biggest innovation in wood in the last decade. When we talked about glue laminated timber before, that was all the laminations were in the same direction.
Right.
Here, we are laminating in orthogonal or 90 degrees to each layer pieces of small lumber, and we can do it in 3 layers, 5 layers, 7 layers,
Right.
9 layers. And that's where we get these 8 feet wide by 60 feet long
Right.
members.
And, I'm looking at this and I'm thinking, for a person to understand what's actually going on here, if you were to take a piece of the old type lamination in which the grain is all going in the same direction, you could actually split that with an axe.
Right.
This thing, it would be a very long day.
Absolutely. But it was really invented in the 90s in Europe, and it can compete cost-wise and structural-wise with poured concrete, with reinforced pre-stressed concrete. The pre-stressed concrete industry can build a building very affordably. Now the pre-stressed laminated timber industry can build these buildings. We can span 30 feet pretty easily with these planks. We can build 20-foot walls pretty easily with these. This is a 3 or 4 story, not 6, condominium that was going up in northern Quebec last year. The company that in Quebec that makes the CLTs, they decided to build some condominiums in town. And so here they were using them for the walls, for the roofs. You can see the floors. Skidmore, Owens and Merrill, obviously prestigious engineering and architecture firm in Chicago, did a timber tower research project where they looked at a building, a concrete building that they designed in the 40s or 50s, that's been built numerous times all over this world. And they said, well, what if we were to do this out of wood using these materials? What are the carbon implications of that?
Now that I'd like to hear about.
Well, this is the sort of the infographic that came with it. As they got into it, they realized that there were some places like this ring beam where they wanted to use concrete for some structural reasons. So they didn't go to, eventually they didn't go to an all wood building, although they could have. But even here, when you look down, comparing timber and conventional structure, this is wood, the orange, the steel is just a little red bar, and then the concrete is here. So the volumes are pretty similar, all concrete and steel, but because the wood is making us so much of the volume, the building weight goes down tremendously.
Interesting.
And when the building weight goes down, that means the foundation needs to be small, can be smaller, and we're not using as much concrete in the foundation as well.
Interesting.
So when you look at the net CO2 emissions coming from each of those, you've got timber actually negative because it's storing, and then the steel and the concrete adding.
So
being
your
positive.
carbon footprint is cut.
Cut dramatically. So the same building out of concrete and steel is 9,500 versus 2,100.
And these are innovations we don't normally take into consideration when we think about saving carbon.
Right.
Well, we've talked about some interesting carbon-saving technology on this show where we're talking about carbon farming and things like that, which most people just don't think about.
Right.
The idea of letting the grass roots go down farther. It's an interesting thing, but we're talking about something that I'm gonna differ with you here. I think this is gonna get sexy.
Well, with enough architects out there, it's definitely going to get
gonna-
starting to get there.
What's going on here? We just lost our feed.
Oh dear. Ah, there we are.
It's
Just
come back.
sleeping.
I think that was the computer objecting to the fact that nobody had touched the mouse.
Yeah, I think you're right.
Okay.
So this project here has been built in Austria. A large Austrian contracting firm that actually does tunnels and highway and sort of civil projects decided that they were going to champion sustainability, and they were going to build a wood skyscraper.
I love it.
and it's going to be to Passive House standard. So here's a cross-section detail of a timber. They actually did go to a concrete composite timber floor system because you can get a little bit more span out of it, and there's some fire rating and serviceability issues there that concrete
Fire
does some
rating
good
is
things.
of course important,
And I
concrete
will
is
talk
nice for
about that. Yeah. But here's the structural model of what the buildings could be, glue lambs, and basically only the basement or only the foundation needs to be reinforced concrete. And here's an example of one of these types of constructions, the same company.
The first thing that came into my mind when I saw that was I could just imagine what Frank Lloyd Wright would have done if he had had this available.
Well, I'll tell you, this architect Hermann Kaufmann, he's got a good hand. He's
a
makes some
bright
beautiful
guy.
stuff.
Yes, absolutely.
And so here's a section again through the office building where you've got this glue lamb concrete composite floor system, and in between it they've developed these prefabricated factory mechanical modules that will slip up in there either to provide heating, ventilation, or lighting. And so everything can get built off-site, and these buildings go up week by week, floor by floor, basically a floor a week, and which is drastically different than what a conventional site-built concrete or steel skyscraper would be. In terms of fire testing, obviously that's one of the biggest things to overcome, but a lot of research has been done on fire testing, and wood has this amazing ability to insulate itself as it burns. It develops a char layer, and that char layer is an insulator and prevents the wood on the core of the beam from charring further. And so you can get out of these buildings before they fall down, basically. And that's only true with the big wood.
Yes.
it's a function
Yes.
of surface to volume
Yes.
ratio.
Yes.
And so 2x4s,
Very
2x6s, those big fires in the cities in 1870s, in the 18s, those were smaller dimensional things burning, not the
Yes.
heavy timber burn.
Yes.
But unfortunately, the codes were written to not allow wood construction above 4, 5, 6 stories. And that's what's currently in our code because of the history of stick framing.
Well, what they should do is they should say, this isn't wood.
Well, that's one approach, but we are changing the code, and we've gotten these cross-laminated timbers and these glue lams. They're in the new versions of the IBC and the IRC, so that they can fall into the heavy timber category of the code. But eventually, we're going to get to the point where it's going to be a performance-based thing, and anything that will just have to satisfy at time.
That is an interesting picture on the right.
Look at these 2 steel melted beams draped over a wood beam. Now, which
That's
type of
really-
building would you rather be in?
Really interesting. The wood beam survived, maintained a certain amount of integrity, and those steels. And of course, as I see that, I think about the World Trade Center collapsing, and the fact that that was just a matter of the steel not being able to, and the concrete not being able to take the heat.
Well, it certainly wasn't wood. So this is stick framing in the lower left, heavy timbers in the upper right. I think you can tell just if you were a smoker, where you'd feel more comfortable lighting up is probably under the heavy timber roof, as opposed to starting a fire over your head.
Well, it's like the difference between between a prairie fire. You know, a lot of my childhood was in Illinois, and we used to hear about prairie fires and forest fires, where the fire takes on different characteristics depending upon what level of the forest is burning.
Right.
And if it's a rapid fire that goes through and just burns the vegetation near the ground, the trees are very likely to survive.
Right.
And those junctions are actually quite pretty.
Yeah, they are.
So a lot of research has been done on heavy timber and CLT and the fire performance of it, and so we can make arguments to local code officials to sort of get around the code case by case, and that's what we have to do these days. The USDA has just, well, they haven't actually announced the rules, but they've announced that there's going to be a competition with $1 million prize to design a timber skyscraper in our country. And this announcement will be coming out probably in the next week. It was supposed to come out in September. Hasn't come out quite yet. But if you're interested, write down U.S. Tall Wood Building Prize Competition and get on the mailing list so you know about it, because I don't want to be the only one entering.
When you win, you can be on the show.
So I'm an engineer, so I always have to talk about calculations, but basically, 50% carbon by weight, that's kilogram of wood is a half kilogram of carbon. You do some molecular math to figure out what that is equal in terms of carbon dioxide.
Oxygen is a lot heavier than carbon, and it's a bigger component. You've got 2 oxygens for every carbon.
Right. So here's some simple, that one everybody can do probably. 1,000 kilograms is 1 metric ton. You do the math with all this, and then you add in that wood basically weighs about 34 pounds a cubic foot. You do some more math, and you figure out that a cubic meter of wood sequesters about 1 metric ton of carbon dioxide. And I like simple one-to-one things to remember, so that's something I can always remember.
I think a lot of people are going to have difficulty visualizing a cubic meter of wood.
It's big.
It's big. It's about 40 inches by 40 inches by 40 inches.
Right. I'm currently designing a school right now in Connecticut that's going to sequester about 500 metric tons of carbon dioxide. So going to have 500 cubic meters of wood.
This is going to be built by Bensonwood?
We sure hope so.
That's a very cool idea.
Yeah. Unfortunately, wood does take some energy to make these products, and so you have to balance that back in. But even with, and it depends on how much processing and drying and glues you're using, but even with the sort of the most engineered wood, there is only about a kilogram of carbon dioxide emitted per kilogram of wood. I just put these down here to show you that steel and concrete and aluminum also emit, and they don't sequester anything.
Right.
So these are the big only emitters. And so when you add the emissions to the sequestering, often, and most often, the wood is still carbon negative cradle to gate. So from the tree to the job site in place. Obviously, what happens after it, if it's burned, that carbon goes back into the atmosphere. If it's buried, it eventually goes back into the atmosphere.
Or not.
Or if it's fixed by something else.
Yeah.
But it could be reused.
Right.
We could take these down.
Right.
And so basically, we're sequestering somewhere between 1 and 1.4 kilograms of carbon dioxide per kilogram of wood.
Right.
And that's the important thing. Steel, concrete, aluminum, you're never going to do that. You're not sequestering anything. We can look at our insulation in the same way. These are some highly toxic to the climate foam insulations. This is the group of other insulations. And when you look at the other insulations blown up, the one with the sort of the best climate performance is the cellulose down here at the bottom. And that's because it's a carbon-based sequestering product.
So the very fact that you're using that insulation means that you're sequestering carbon.
Right.
Now this is important for people to know.
Right. And carbon is important. And so here's a plot of what's going on in a piece of wood as it grows. For the first, as it starts to grow, it actually is going to give off a little more carbon than it emits. But eventually that passes back to the negative. It sequesters as that tree gets bigger, bigger, bigger. It's cut down. This is the processing energy. It's not doing anything while it's in use. And then whether it's burned, recycled, reused, or put in a landfill. And as long as when you cut this down, you're growing other trees, we're continually fixing carbon from the atmosphere. And so this is a graph from Cree, the 30-story building I was showing you before, where when they looked at carbon in their building, they actually found that the whole building was carbon negative, or nearly carbon negative, 92% of a wood building versus a concrete building. So this is 90%. I think SOM came up with 75, 80%. So we're talking about significant reductions. And and that's what reinforces the message that Journal of Forestry, 34% of carbon emissions if we went to all wood construction instead of steel and concrete. It's a big amount of carbon.
Yeah, it is.
The last time we had time to actually look at our board foot total of wood at Bensonwood was 2004. It probably hasn't changed too much, although it is now increasing again after this little downturn in the economy. We break it down by timber framing, dimensional lumber, engineered lumber, which is the glue lambs and I-joists, and then our fine high-end woodworking. And so annually we were sequestering 625 metric tons of carbon dioxide. There's a spreadsheet I've written to help me analyze it anytime I want. And I think the important thing is to know where your wood's coming from. When we're using the large solid sawn timbers, we're buying it from this small company in Oregon, and what they're doing is they're harvesting standing dead trees that were burned in fires. So we're not cutting down thriving ecosystems, we're cutting down something that was burned. And they're not cutting down all of it either.
And of course the wood isn't damaged in the fire.
Right.
For exactly the reason that you were talking about earlier.
Right.
The char insulates it. And of course one other thing too is that it's loaded with water. So, and it's hard to get that water to be converted to steam, which is what you've got to do before the wood will burn. So this wood is as good as any other wood that's out there.
Right. It's actually better because it's drier. And so it's going to move less as it comes to its final equilibrium moisture content.
Yes.
So these are what their job sites look like. This is what their sawmill looks like. We know these people very well. Now, sort of on the other end of the spectrum is this company up in Canada where we buy a lot of our engineered wood products from. This is their plant in northern Quebec. These are all bundles that go on trucks of engineered lumber. And this is an aerial picture of their forestry operations. You can see all these little baby trees growing. And this company is 4 generations old, so now they're cutting the trees that their grandparents or great-great-grandparents were planted 4 generations ago. So Bensonwood has recently joined the FSC certification chain of custody group. FSC is the Forest Stewardship Council. It is the only independent, non-industry sponsored, LEED recognized forest stewardship certification available.
Right. And that LEED recognized says a lot. Anybody who's listening, watching, should understand that really says a lot.
Right. And it's actually more than just the forest. It's about the indigenous populations. It's and making sure that they're not being taken advantage of, or slave lumber or whatever.
Yeah, exactly.
And it's about education, getting people to understand the importance of proper forestry.
All of which gets included in some of these standards.
Right.
If you're using your LEED building to educate people, that's part of the standard.
This is an exhibit that actually just closed last week down in Boston that had a lot of great infographics about wood and urban environments and how it can save the world with carbon sequestration. It will most likely be opening up again on the UMass campus, although it might be somewhere else. UMass actually is going to be building a heavy timber building, 5 stories tall, in the next 2-3 years. The state legislature just appropriated, I think, $3 million as a timber demonstration project.
Very nice.
And this is a project that I did the engineering with a team of architects out of New York City, all made out of this cross-laminated timber. So I'll just show you some of my favorite projects, because I like to.
Yeah. Does anybody know what time we started this segment? Do you know, Tom?
I think we've gone over an hour.
I don't think we have, actually.
I think we're good.
I think we're right around
Well,
there.
I think we're right around
Keep
it.
going. Let them
Oh my goodness gracious! Look at that.
So this is actually the steeple right next door here in Brattleboro.
Is it really?
Yeah,
Yes.
This is looking up it in our shop. This is our prefabricated steeple. We loaded it onto a truck horizontally, and we picked it up in one pick of the crane and put it up in the air.
Interesting?
Yeah, it's a
Isn't
block
that-
from here.
We drove by it on our way.
I had the copper ball on my desk for 3 months.
Wow.
But this was all engineered glue lam timbers. This is Douglas fir. And then we used local hemlock to sheathe it, because hemlock is abundant here, and we didn't need the engineered properties.
Yeah, and unfortunately, hemlock will not be abundant here for very much longer. I'm
Not with the
afraid.
woody adelgid, no,
No.
but it does hold the slate real well.
And we can blame climate change for that if we want to. And anybody who says climate change isn't really there should
Is
go
wrong.
out and talk to a woody adelgid.
Oh, here's some of those. There's the long, 8-foot wide, 60-foot. That was a 30-foot plank.
A 30-foot plank.
That's 3 stories.
Ladies and gentlemen, here you see a single plank, 30 feet long, and what is that, 8 feet wide?
8 feet wide.
And 1 foot thick.
Wow.
And you need to have a fairly heavy piece of equipment to move it, because it's not the sort of thing you can throw in the back of a pickup truck.
Right.
And the other side of it is identical, but they shaped it.
Well, this one went up to the roof. It had a doorway in it, and these 2 holes are for some spiral duct that winds up going through it in the end.
So it's basically the same thing.
It's the
8
same
feet wide,
thing, yeah.
30 feet
Yep.
long.
There were 3 of them in the building. And we were able to make some connections to the beams. And this is a gallery down in Brooklyn, New York, inside of an old, garage or something. So we were building the ship in the bottle here, also made out of cross-laminated timber. You can see the cross-laminations on the edge grain here. Quite a beautiful little space.
Here's some more crux.
Here's some glue laminated curves that we fabricated. Actually, these are not curves. I'm sorry. We would have liked to make these out of curves, because then you can have the fibers being continuous, but the client didn't want that. So we had to make a scarf joint in the middle of this thing, and that's what that peg and those two cherry keys and that peg are about. So these are sawn, two pieces that were sawn, and we didn't want to do it out of one because that would have been just the removal of too much fiber. The structure couldn't handle it. So again, fabricating it in our shop, pre-fitting everything, making sure it's going to go together quickly. And this was another ship in the bottle where we were installing this from underneath. Here's the Pat's Peak ski pavilion that went in a couple years ago over at Pat's Peak in Henniker. This is a large carport made out of glue lambs down in Pennsylvania in the Poconos.
Amazing. This is all amazing.
This is a 70-foot long roof for a church, 70 feet across, 3-dimensional truss, building in the shop and then building it again on the parking lot. And then this really it speaks to me the most about the craftsmanship of our team and the ability to bring 1, 2, 3, 4, 5, 6, 7 pieces of wood and land them all on the top of one post with the joints that tight. It's just incredible. And that commitment to quality is what permeates our whole company, whether it's about the timber joinery or a non-toxic, non-polluting wood solution or an environmentally better building envelope or window design. That's what we are about. So again, we can save, using wood, 14 to 31% of carbon dioxide emissions globally.
Great.
Yeah. So, sorry I went on so long. Rhiannon didn't get to tell you much about what she does.
Well, you can come back sometime. You can tell us later. I think we'd better say goodbye. I don't know that they're going to be able to get this into a single hour.
They'll figure out some way to splice it.
I suppose, but anyway.
Well, this has been very, very educational. I really want to thank you. I enjoyed it very much. I hope our audience did. I'm sure they will.
We spin and we toil, we work all day, sowing and reaping, we store goods away, so we can be dressed well on the day that we die.